Previously, we looked at the theory behind how to put together an electric field and a magnetic field together and do some kind of particle manipulation. Now, let's go try apply some of these ideas to some past year questions. Now, if you have not tried the past years yet, go at least try it out. This one's on page 39, MJ20, P42, Q9, and the one after this. Go check the video description to see what the other one is. Try it out. Never mind if you get stuck. Stuck already, you come and we look at it sections together. So, an electron is traveling at a speed in a straight line in a vacuum. Enters a uniform magnetic field of magnetic flux density. When you see this, right there, B. That's a piece of information they give you. You probably need to use it later. Now, initially, the electron is traveling at right angles to the magnetic field. So, magnetic field is probably out of the page or into the page, as illustrated. Okay, so where is the electric field pointing? Can we kind of figure out where it is pointing? Well, you see, first thing is an electron. So be very careful. When you see negative charge, sign the warning flag. It's an electron. And the magnetic force, it looks like it's going to act this way downwards. Because the particle curved down. So magnetic force got to somehow be pulling it down into a curved path. So you could try to do this. At this particular point in the field, the particle is moving to the right, but you got to stick your left hand to the left. Sorry, left hand. What am I saying? Middle finger. Okay, let's do this again. This is your thumb. And the velocity of the particle is going to the right. But because this is an electron, this thing to the right is where a positive charge will go, right? So you need to put your middle finger pointing to the left. Because that's where a positive charge would go. And that's what we use for our Fleming's left-hand rule. So you point your thumb down, twist your arm so the middle finger is to the left, and you see you should be pointing into the page, which means this magnetic field should be into the page. Okay, so be careful with electrons. Reverse. If you can't forgot already, or you're going to review a little bit your force on particles. Okay, your Fleming's left-hand rule only shows the direction of the positive charge. So if it's a negative charge, you gotta bend your middle finger backwards, which doesn't really work. Okay, so you gotta rotate your hand. Okay, let's see. The path of the electron is in the arc of a circle. So yes, magnetic field, circular motion, radius 6.4. State and explain the direction of the magnetic field. Hey, we just did that. Use the hand, adjust a little bit. Let me see if I can find a diagram. There's our picture reminder, F, B, and V. Fleming left-hand rule. So we need to explain that a little bit. But also, let me tell you a tip. If you find the electron messes with your brain too much, it's like, Miss, I cannot twist my hand because of the electron and I don't know how. So this V here in the diagram, this middle finger V is where a positive charge will go. But this is a negative charge, so you need to reverse the direction of V when you're using your left-hand rule. So if this messes with you, use your right-hand rule. So left hand for positive charge, right hand if it's a negative charge. This is a shortcut and you can use it only if you know what you're doing, okay? If not, you'll be like, why got left hand, right hand? Because later there'll be another right hand. So yeah, if you find it hard to think about electrons, left hand rule, remember, it's a positive charge. That's a middle finger where it's going. Then your right hand rule, well, left hand rule but flipped. That's because Fleming's left hand rule but flipped the other side. That would be your right hand rule for negative charges. I mean, if that works for you, sure, use that. But if not, then just stick with your left hand so you don't get confused. Okay, but try it out. Your right hand, point your middle finger to the, what you call this? If you're using your right hand, then you can point your middle finger here. But anyway, that's just a side note. If you're confused, just comment, ask me about it. But anyway, we need to explain, right? How do we know whether the magnetic field is pointing into the page? Okay, so we gotta explain that we're using our Fleming's left-hand rule and talk about it. So, what do we say? State, explain. Where is the magnetic field direction and why do you say it is in that direction? So you can say magnetic field is into the page. That is your answer to the state or the where. But then you must say why you say into the page. Well, then you can say into the page because or by Fleming's Gotta name drop, gotta mention the name. By Fleming's left-hand rule. Okay, and you talk about how you use Fleming's left-hand rule. So talk about the force, talk about the direction of the particle. So let's just state all those. Because force is downwards, that's your thumb, and current is to the left, that's your middle finger. Okay, wow, it's a long one. First one, magnetic field into the page, left, Fleming's rule, that is the first one. Second one, you talk about the details of the other fingers, force and the current. Which side is it? Okay, so remember, you see, they notice they use the word current. That's because, you see, electron moving to the right means current is moving to the left. Because current, we define as positive charge moving. So when you use your left hand rule, you gotta point your middle finger to the left. Don't forget, this is electron. Be very, very careful. You're pointing your middle finger to the left, which is the direction of a current. Okay, so reminder, warning. What else can I draw here? Warning, reminder. Okay, moving on. Show that the speed of the electron is 9 times 10 to the power of 6. Wow, how to show the speed? This is what magnetic field, right? We know B. Oh, we want to find the speed V. What information do we have? Radius. Okay, we know the radius. But we need more information. Maybe we cannot do this. No, not B. We usually would think of this, right? VQV sine theta or sine 90. So this one's gone. But we want to find V, but we don't know F at the same time. So we don't have a lot of information to help us out here. So we can't just use BQV sine theta alone. But remember, particles in the field is going to go in a circular motion with a radius. Wonder why they gave this piece of information right up here. So let's do that. So the magnetic force provides the centripetal force. Centripetal force is from chapter 7, remember? So we need to say, oh, BQV. I'm going to say theta is 90 degree because this whole electron path, this whole plane is right angle to B. So I will say, V is always perpendicular to B because they are in different planes. One is flat, one is out of the table into the table. So don't worry about that now. So we have that and mv squared over r. The v's here are the same or not? Yes, they are tangential speeds at every point along the curved path. So we can say, let's cancel out v, divide both sides by v. What we have is bq equals to mv over r. We want to find what? Speed of electron. Okay, let's rearrange. So you rearrange that, you should get v equals to rbq over m. Oh, square root. Square root. Don't need to square root lah. We already cancel out one side of the v, so there's no square root. It's just rbq over m. So let's plug in everything we know. They give us the answer already, right? So we just need to make sure we get that. Okay, long plugging time. So I'm gonna write it down here. So we'll have the radius. They gave it to us as 6.4 cm. So make sure you convert to 10⁻² meters. B, they give to us the magnetic flux density, right? 8 times 10⁻⁴, right up here. So that will be 8 times 10⁻⁴ Tesla. What's the Q? What's the charge of an electron? Q will be E, which is a constant. And you can find that E on the first page of every question paper, which is 1.6 times 10⁻⁹. Elementary charge of an electron. Okay, let's try to draw another straighter line. Okay, that's better. Mass. What's the mass of a particle? Electron here, our little friend, also has another constant. So if you look in the front page, once again, data formula sheet, mass of electron, I think it's written as ME. That will be 9.11 times 10⁻31 kg. So you want to write that down in your working time, 10⁻31 kg. Okay. Whew. Finally, press calculator. You should get about 8.99 times 10. Very fast speed. Whoa. Wow. That is pretty fast. So 8.99, when you round it off, it's about 9.0. Okay. Pretty good. We got our answer then. So 3 marks. A nice big fat 3 marks. First one comes from you knowing what provides the centripetal force that allows this particle to go in a curve. That will be the first C1 mark. You can also explain it in a sentence, like centripetal force, magnetic force provides centripetal force. So I'll just write here, magnetic force provides, especially when they say explain your working, oh, you gotta write out some sentences. So magnetic force provides centripetal force. That is explaining in a sentence. Then the second mark comes from you equating both expressions for magnetic force and also centripetal force. So that will be BQ, V equals to mv squared over R. Then the last one is you plug everything, okay, you get your answer. Okay, can now lah. Plug in all the correct values and get your answer. So that is this part to show the speed of the electron. Moving on. Now is when interesting things happen. A particle oops, sorry, wrong side. This one here, I was like, hey, why did it suddenly change one? A uniform field now is applied. Uniform electric field. Guess who joined the game? Electric field. So just now it was magnetic field, now got electric field some more. Now electric field is applied to the same square region down there. Electron now passes undeviated through the region. Undeviated means no deflection, no curving, no just straight line going through, sailing through there. On figure 9.2, mark with an arrow the direction of the uniform electric field. Okay, let's transfer the direction of force first. So we know magnetic force is going to be pointing downwards, right? So let's just remind ourselves that, hey, magnetic force is downwards. And that would cause the particle to usually curve down, like, in the front other section there. And magnetic field is going to be here inside also. I'll just put some X's to remind ourselves there is a magnetic field into the page. But what's new is an electric field. Where do you think the force is pointing? You gotta counter the magnetic force, so of course electric force will have to be pointing upwards. So this would be your electric force. Okay, so they asked us to draw what? Uniform electric field. Oh, not the force, they want us to draw the field. Okay, nah. Then we shall draw. Alright, an electron going up. That means the field must be pointing down. So let's draw some electric field. Straight lines pointing down. Use a ruler, okay? If you guys have a ruler, just use a ruler. Draw like a few equally spaced arrows to represent the electric field. Now, if you're saying, Miss, why electric field point down? I thought it should point up. Hey, hang on a second. Gotta review your electric field chapter a bit. So if you have a high potential and then to a low potential plate, this is kind of like the positive plate to a negative plate. Where is the electron going to go? Upwards. Because don't forget, electrons' force is opposite to the electric field. Come on, let's do a bit of revision. If this is the electric field and this is an electron, it will go against the electric field and be a rebel. Only a positive charge would go with the electric field. See the difference? Okay, so yeah lah. You just remember this. Remember this, okay? So an electron wants to go down due to magnetic field, but electric force is kind of keeping it up, so it's going in a nice straight line. Okay, 1 mark if you got your electric field pointing downwards. You got that in the correct direction. Now let's look at the next part. Use the data to calculate the magnitude of the electric field strength. Find the E. Use data from A. So if you remember the theory, we talked about this. How do you keep both of this electric field and magnetic field together? The key is to think about the forces acting on the particle. You have your electron. Magnetic force is trying to pull it down, but that is cancelled off by the electric force, which is now pulling it upwards. And these two forces should be in equal magnitude, opposite directions, because the path of the electron is not changing. So you can say, all right, let's let's talk about this. Electric force and magnetic force should be the same magnitude. So that means I can say BQV sine theta, but theta and theta is 90 degrees, so sine theta is 1. And QE should be equal. Q is cancelled out, divide both sides by Q. So all that's left is BV equals to E. So we want to find electric field strength, right? So we take B times V. What is the B? Is it the same B? Yep, it's the same B from before. So check your previous section. What do you use for the magnetic flux density? That's 8 times 10 to the negative 4. What is this V? Velocity. V also used from before. So the one that they asked you to show, that will be 9.0 times 10. Was it 6? 10 to the 6, yeah. So electric field strength will be 7200. Final answer here, I'm going to put in standard form. So this will be 123 times 10 to the 3. Okay. So 2 marks. 1 is final answer. Accuracy. A for accuracy. Second one is, do you know this thing or not? Go from here to here. Equate both forces because they have to be equal magnitudes. And you simplify to BV equals to E. This is how you use the equation. Okay. Next. Electron is now replaced by an alpha particle, same speed. Wow, alpha particle is different. Okay. Same initial speed, that's important. Describe and explain. So you must say how it looks like and why you say that. Explain is the why. This one is the how. The shape of the path. This is what we're trying to describe and explain. Inside the region. How is it different? Here, an electron come in. Now you have an alpha particle coming in. What's the difference between electron and alpha particle? Well, if you think about it, remember we mentioned in the theory video, in this kind of system, the only thing that will make a difference is the initial velocity of the particle. What velocity you come in will affect whether you curve or not. Okay? And if you're wondering why, take a look at this. Magnetic force is BQV. Electric force is QE. So in terms of the particle itself, Q and Q will cancel out, will balance out. The only thing that is going to affect a particle's path is going to be this V. This deflection will be the V. If the V is the same, then it should be the same exact path. There should be no deviation. So you can say path is a straight line and not deviated also. So undeviated as well. Okay, and then you got to explain why you say that. So you got to mention that the condition. This way you kind of explain a bit. So they say, what affects the path actually is the initial velocity. The charge both will cancel out. So the condition for deflection in a field, magnetic or electric field in this kind of setup is only dependent on V. Only depends on velocity, speed V. Use their same language lah, speed V. So if they have the same V, they're going to have the same path. Okay, if you want to add on, you can say it's independent of M and Q. You say, it doesn't depend on the mass. Alright, so the 2 marks here, one is you say it's undeviated. Second one, if you explain a little bit, only depends on speed V. If you're not convinced, draw a table lah. Say, okay, let's compare the mass and the charge and the speed of a particle. Firstly, we have electron, right? Then after that, we have an alpha particle. Draw a table lah. I mean, don't have to do this during exam, but for now, since we're practicing, let's look at the difference a little bit. Revision of what is alpha particle. So electron, the mass is ME, very small. Alpha particle is what? 2 proton, 2 neutron. We always say 4U, atomic mass unit, is another constant you can check in the question paper. So the alpha particle is much heavier. But any of this equation, you got see M? No M also. So it doesn't affect, don't care, M doesn't affect the path. of this setup, I say. The charge. Electron is negative 1e. Alpha particle will be positive 2e. Okay, so once you change to alpha particle, you have a larger magnetic force, but also a larger electric force. So when Q increase, both your Fe will increase and your Fb also increase. And don't forget, Fe, Fb, they are cancelling each other out. 1 points up, 1 points down. So the effect cancel out lor, once you upgrade to 2e. How about the speed? They have the same speed, right? Still V, still V. Okay, then no change lah. Okay, so what we were describing up there is that this one, the speed, is what will really affect the path. Alright, so keep that in mind because there are two forces acting here, so make sure you can know how to think about both of them. Don't worry, plenty of more past years to try it out. Okay, next question. You'll find it in the next video, example video, so go try it out first. So that you have kind of an idea of how to do it. Try it out first, then join me in the next example video and we'll look through that question together.